tell me if it's... Is it working?
You're rocking.
Okay. Are we ready?
You're ready.
All right, guys. So, as Dr. Carmen said, my name is Jennifer Hubbard-Sanchez. I work at Kentucky State University. I have two very different full-time jobs. One is doing environmental education trainings. Some of you I've actually had in my workshops before across the state. I do teach a lot about climate change. And the other job is I serve as the manager of our Environmental Education and Research Center, which is located in Henry County, a little bit northwest, about 30 minutes northwest of downtown Frankfort. So I was just telling Carmen my latest debacle. I found out from Fish and Wildlife last week that we now have wild boars in our area. So besides teaching about climate change, now I'm going to become a wild boar hunter, which scares the crap out of me, but that'll be fine. So today I am here to talk to you guys about climate change. And the best way to do it is to really just start at the very beginning. So just to start, for you all, how comfortable do you feel with the science of climate change? If you're a 5 out of 5, raise your hand. If you're a 1 out of 5, raise your hand. 3 out of 5?
What is the scale?
Scale is 1 to 5, 5 being the highest.
Oh, like you're confident.
You're very confident, like you could teach a whole class on climate change. Anybody feel any way about climate change? Anybody? No? All right.
Everybody's looking around the room to see how they else.
I know, right? Like I mean, if we expected you to know a whole bunch.
3.5.
3.5?
3.5.
Okay, all right. Well then some of this, we have a lot to pack into about 43 minutes. So some of this I'm not going to focus on very much. But if we get to a point where you're just like, what did you just say? Let me know, stop me, interrupt me. I'm very informal, and so I don't mind if you guys have questions. I will say, typically when you're teaching about climate change, the first thing you teach about is weather, and I apologize that this week you're learning about climate change first and weather on Friday. It was a scheduling issue, so normally you guys would have done your weather session first, but today you're doing climate. So we are going to start. Maybe if I can get this thing working, with an overview. What we're looking at today is just understanding the basics of climate change. A lot of people have this idea in their heads, but when you ask them to define it or describe it, it's really hard to break down. And so we're just breaking it down to the simplest form. We're going to talk about the causes of climate change. We're going to talk about the naysayers. I don't know if you guys know there's a big secret in 2018 in the United States, but we're having a hard time agreeing on too much. Unfortunately, climate change, which is probably what I would consider the issue of this generation, my children's generation, is one of those things that we continue to argue about in our country. Most other countries, there's no argument. They're looking at ways to mitigate the issue, whereas in the United States, we're still, the jury's out on climate change, right? We still don't know if it's happening or not. So we're going to talk about the naysayers and how we know what we know, because that's a question that comes up often. And then we're going to talk about projections for future impacts. Where are most of you from? Kentucky? Raise your hands. So for those of you who are not from Kentucky, where are you from?
China.
From China? Who else? Washington, D.C.? Who else didn't raise their hand? Everybody else is from Kentucky. All right, the projections we're going to look at today are pretty much this region, Kentucky, Ohio, and Indiana. So we're looking at very specific local projections of impacts. So weather versus climate, off the bat, who can define it for me? What's the difference between weather and climate? Right? It's hard to just put into words. Go ahead, ma'am.
Say weather is kind of like day to day, where climate is like the overall.
Exactly. So weather is what we experience, quote, day to day, is exactly what you just said. It's what's happening today versus the rain-mageddon that we suffered through last week and the week before that and the week before that. Day to day, or season by season, climate is really a long-term average of those day-to-day weather conditions. A lot of people say, weather tells me what to wear. So when I went outside today, I knew that it was going to be 82 degrees and I was going to wear something that wasn't too hot. Climate tells me what to buy. So if in April and May, when all of the really good clothes were going on sale at Cabela's, and I thought, ooh, what am I gonna wear for work in October and November? I would have thought 50s and 60s, right? That's how you know what to buy for the next season. Whereas I walked outside today and realized, no, summer is still here, it's still hot. So weather tells me what to wear day by day, climate tells me what to buy. And then the last metaphor is climate is personality. So it's ideally this pretty steady, dependable kind of, we know this is the way it's gonna be. And weather is mood. If you ask my husband, I have a certain climate, but I also have lots of different moods. Even Carmen knows that. So again, just to summarize, weather are the immediate atmospheric conditions, what's happening outside right now, and it's in the short term. Climate is an average of weather over time and space. So scientists used to look at about 30 years of weather data. And they would say, okay, if you are from China, or you are from Washington, D.C., or you're from Kentucky, what are the average atmospheric conditions in any given time and place in January, June, February, whenever? And that's how they would come up with what you would think, this is the climate of that region. Today, it's kind of harder. As you guys know, things have changed really quickly the last 10, 15 years. We've had some of the hottest years on record, the wettest years on record, just in the last 5, 6, 7 years. So when you still look at that long-term average, it may look like it always has, but then when you look at year by year, things are changing pretty quickly. Climate is what you expect and weather is what you get. So the definition of climate change refers to any significant change in the measures of climate, so that day-to-day average that lasts for an extended period of time. It includes major changes in temperature. Again, we've had some of the hottest years on record across the country the last, I want to say about 15 years. Precipitation, Kentucky, just in the last few months, it's been one of the wettest summer, fall sort of seasons that we've seen in a long time. Wind patterns, among other effects that occur over several decades or longer. This is sort of the historic, like I said, definition of climate change. It's getting harder for scientists to look at that long-term period because things are so up and down right now. So the usual weather found in a place, which would be looking at things like how much rainfall, the usual temperature of a season. I always just put silly, snarky things in my PowerPoints because it's how I feel about this whole issue. Sorry. So what causes it? Anybody want to take a stab at that before we move ahead to the next slide? What causes the actual warming of the Earth? Greenhouse gases. Can you explain it all, how it would happen? And you don't have to if you don't want. It's early.
They basically like insulate the Earth, so the light that hits the Earth can't leave, and it's trapped and just keeps heating up in a cycle.
Yeah. So the greenhouse gases are literally trapping heat into the atmosphere. If you guys look here, I really like this very simple graph. So typically, you have your solar energy that's coming in. You've got a blanket of gases, and it is a naturally occurring thing. Greenhouse gases are what has allowed humans and other species to thrive on this planet. Sunlight comes through, it warms the surface of the Earth, and then that heat radiates back into space. Right now, what's happening is that heat, this layer, if you guys look at this orange layer, those are your greenhouse gases. In a natural system, solar radiation comes in, it's re-radiated. A significant amount is escaping back into space. However, because of this thicker blanket here, more greenhouse gases in the atmosphere, what's happening is a smaller amount is being re-radiated. It's being trapped right here. And so what that's doing is causing the heat to stay and to cause what's called global warming. A lot of people use climate change and global warming interchangeably. I think that an easier way to think about that, this is global warming, right? We're warming the globe. However, that warming phenomena is what's causing changes in our climate. So 30 years ago, when I was, however old I was 30 years ago, I don't want to tell, we just called it global warming. Do you remember that, Carmen? When we just called it global warming, but we weren't seeing as many drastic changes. Today, a lot of people still use global warming to define what is actually climate change, which are those changes in temperature, rainfall, all of those different impacts.
Well, I think it also caught the word climate change invokes in more people's mind that impact of global warming maybe doesn't do so much with climate change. We think, okay, here's the actual result of these actions.
Things are happening, yeah. But some people don't even recognize that difference, and that's a problem. So this is, a very elementary school way of thinking about it. And it's funny to do this on a day like today, but pretend we're in December and it's 40 degrees out. You walk home, you go to your house, you put a blanket around yourself, and you can feel that heat trapped in your blanket. If you add another blanket and another blanket and another blanket, all of that heat is staying trapped in. It's the exact same thing with what's going on right now in our atmosphere. Gases that trap heat near the surface do the exact same thing. So less of that heat is escaping and more of it is staying here toward the Earth's surface, which is called the greenhouse effect. Why is it occurring? Ideas? So we know what's occurring, but why is that occurring?
More CO2 in the atmosphere.
More CO2 through what? What's
Fossil fuel burning.
burning of fossil fuel. What are some of the other greenhouse gases? Anybody want to take a guess? Methane. And where is that coming from? Exactly. But we all need to eat, right? I mean, it's one of those kind of catch-22 situations where we know this is happening, but somebody's got to keep McDonald's in business, So why is it occurring? Human activities are now the major cause of most of the ongoing increase in our globally average surface temperature. Effects in recent history have been caused by human emissions of greenhouse gases. So burning of fossil fuels, which would be oil, natural gas, and coal. Clearing of forests, that's kind of that opposite effect. We're not burning anything, but we're literally cutting down the lungs of the earth, right? So the more that we deforest, the more land use changes we have, the less carbon dioxide especially is being absorbed. So not only are we emitting more, but we've interrupted the Earth's process of being able to absorb that CO2, right? There's more going out and less being absorbed. Nitrogen fertilizer used for crops, production of industrial products, and decomposing waste in landfills, agriculture, and actually rice cultivation is one of the biggest contributors toward methane in our atmosphere. Who doesn't like rice though, right? I mean, it's... So greenhouse gas emissions, these two graphs, I don't know if you guys, can you read them from the back? Probably not, right? I'll kind of point them out to you then. This was the most recent 2014 global carbon emissions from fossil fuel combustion. Now this one takes it country by country, and this has changed significantly from, I think there's a 2009 version of this graph. So China emits 30% of all global carbon dioxide. The US, 15%. European Union, 9%. India, 7%. Russian Federation, 5%. Japan, 4%. And all other countries account for 30%. Now, when you look at this, and I don't want to go getting all political on you guys, but when you think about what we hear in the news all the time, oh, but China. Oh, but China. We're not going to do anything until China does, right? Have you guys not heard that in public speak? What's the difference between the United States at 15% and China at 30%?
China is still a developing nation. They're kind of coming into industry on their own, whereas the U.S. is past that phase. So it's harder to tell China to stop what they're doing, even though that's not
and there are a lot of, you're right on that, there are a lot of countries that they call them, we call them leapfrog technologies. We want to encourage other countries to not use the technology that we've always used and that we've benefited from cheaply and easily. We want to tell other countries, no, you can't do this. However, the big difference between China and the United States is China has 4 times the population that we do. There are something like 3.4 billion people. You're from China, right? You said? How many people are in China?
About like 16 billion.
No, because there's only 7.5 billion on Earth. I think China is is it 3.5?
India's going to overtake them, so they have to be 1 point something.
You think?
If they were 3 point something, then India would be the rest of the global population.
Will somebody Google how many people there are in China?
379 billion.
1.379? And how many people are in the United States? 350 million. Oh yeah, China it's 4 times the United States. We're 350 million times 4 is 1.5 billion. So we, in the United States, are emitting half of what China is, but we also only represent a quarter of the Chinese population by numbers. And on top of that, maybe not so much now, but historically speaking, where do most of our products come from?
China.
So a lot of that, those emissions are due to our consumption. We're blaming the Chinese. However, I go look in my kitchen and half the stuff in my kitchen was made in China, right? So the public speak on whose fault is always blame China, but really, when you do the numbers and you look at the math, we're emitting 4 times as much per capita, per person, than China. This second one here just breaks down for you greenhouse gas emissions by sector in the United States. So electricity and heat production, and agriculture, forestry, and other land use. I always argue when people say there's nothing we can do about climate change. When you look at heat production, I firmly believe if every person in the United States looked at their heat production consumption in their homes, especially in places like Kentucky, because where do we get our heat from? Coal, right? I always have people that say, well, no, we can get it from solar, but do you get it from solar? Does anybody here have solar panels? Can anybody afford solar panels? I can't. I'd love to, but I can't. So in the meantime, I'm depending on coal just like the next guy. A quarter of our greenhouse gas emissions in the United States are coming solely from electric and heat production. Ag, 24%, buildings, 6%, transportation is 14%, industry is 21%, and other energy is 10%. So that's just a breakdown to see where our emissions are coming from. So how do we know what we know? That's sort of like the basics of climate change. Now, how do we know what we know? Where do we get the information on climate, past climate from? Anyone have any ideas? Any ideas? Any ideas? Ma'am?
Like cores from the Arctic and stuff.
Mm-hmm. Ice core samples? Yep. Any other ideas? All right, we're going to learn. So first of all, this is just to kind of illustrate to you all. Anybody want to take a stab at this? Don't overthink it. Carbon cycle, right? Our carbon cycle, right? The human carbon cycle. So what we know is that about 200 million years ago, plants, animals, grown by the sun through photosynthesis, were buried and trapped. And over a long period of heat and time and pressure, those animals, that decaying animal matter, became what? What? Coal, oil, natural gas. So that's, our fossil fuels were developed over a really long period of time. In a relatively short period of time, like 160, 200 years, we've been able to extract most of this from Earth, burn it. We've released all of that CO2 through our usage back into the atmosphere. So what took 200 million years to produce all of that CO2 that was trapped for 200 million years, humans have taken back out of the ground, burned, and re-released very quickly in a period of about 200 years since the Industrial Revolution. We've released that back into the atmosphere. One of the things that people often talk about, and you know, the naysayer thing, the people that are like, no, this is impossible, it's not happening, how do you know? One of the things that we look at are the cycles and what was in the atmosphere. What do you guys notice about this here over the last 400 years? Was it all over the place? There's a cyclical sort of pattern to it, right? CO2 in periods of about 50,000 years would fluctuate down and up, down and up, down and up. And then what do you see here? A spike. And it's gone way beyond. Now this graph is from, I'm trying to think of what year. This says 2000, so we were still under 400 parts per million of carbon dioxide. Right now we're at 406 as of May of this year, so we're right above that line. So what we've seen is it's gone up and down, up and down, up and down, and then all of a sudden with the Industrial Revolution and the development of our technologies, that number has gone up significantly in a very short period of time. So since the Industrial Revolution, carbon dioxide has risen by about 40% in a short period. Does anybody know, anybody ever heard of the Mauna Loa Observatory? What do you know about that? I have some people adamantly nodding. What's Mauna Loa?
It's a giant weather station in Hawaii.
Yeah, and it's been around since the late 50s, 1958. So since 1958, we've seen parts per million of carbon dioxide go up now almost 100 points in, somebody do the math, 70 years, 1958 to 2018. Is that 70 years? 60 years? I wasn't a math major, sorry. 60 years, we've seen it go up 40%, very, 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 very quickly. The Mauna Loa project, like I said, has been going on since 1958. There was question about their funding. I know it's still going on right now, but I think it's kind of on the chopping block for being defunded. So hopefully we can still continue to depend on it. And it's not just carbon dioxide. We focus a lot on CO2 when we talk about climate change. Why do you all think that is? Any ideas on why CO2 kind of gets the bad rap?
Is it because it's the easiest to detect and monitor?
Good try. There's kind of two reasons. Number one, because it's the most abundant greenhouse gas. It's the one that we emit the most. But also it's the one that lasts in our atmosphere for the longest amount of time. So what my great-grandmother, who was born in 1886, what they were emitting in 1886 is potentially still in our atmosphere today, which means what we're emitting right now will still be in our atmosphere in 2118. So it doesn't break down as easy as the other greenhouse gases, which means the effects of it are longer term. When you look at that rise, when you look at this graph and how it's gone up, and when you look at this graph and how this has gone up, we see that it's not just CO2 following that same pattern. This graph right here shows the population of the Earth in billions. You see that curve. Carbon dioxide going up, nitrous oxide going up, methane, and our temperature change, average temperature change. All of these different indicators follow the exact same curve, right? And that's how scientists are able to look and say, okay, maybe it is us. These are things that we're emitting. These are things our activities are responsible for. And as there are more of us, all of these things are going up, as well as average surface temperature on the Earth. So how do we know what was in the atmosphere 400,000 years ago? And you have said ice cores. Scientists, you know, again, you talk to people, and Carmen, you know, we've talked about this in different workshops with some pretty interesting people who, this is the question that they ask. But how do scientists know? Nobody was around 400,000 years ago. And so like you said, scientists use what's called proxy data. And proxy data really is, it's in the absence of being there and being able to measure, we look at other indicators. The way that NOAA defines it is anything in the Earth system that sensitively responds to environmental conditions and is preserved over time. And there are lots of different ways